Assalamu alaikum, my friends. This is Rusty Waller from the Teaching and Learning Center in the American University of Ras Al Khaimah in the United Arab Emirates. And in this video, we're going to begin examining confidence intervals. I just love this little quote that says 98% of all statistics are made up. Wonder if that might be one of the 98%. Now, establishing confidence intervals using z-score boundaries will be the goal of this video. But to understand this, let's go back and dissect it just a minute. Z-score. Do you remember that a z-score is the number of standard deviations that a datum lies either above or below the mean? Those above the mean are positive, those below the mean are negative. Now, confidence intervals establishes an idea that we're going to use z-scores on a curve to determine how we might trap a certain amount of data within those boundaries. A definition of confidence. Confidence is generally described as the state of being certain that a hypothesis or prediction is correct. Now, I've thrown a new word at you, hypothesis. A hypothesis is a statement or a prediction. And confidence levels will be to determine if we think that confidence or that hypothesis is correct. So a confidence interval can change as problems change. How confident do we need to be for several problems? Of course, the answer depends on the situation. Some situations are just not as critical as others, and let me share several of these with you. Hypothesis, I will live through today. Now, for me, that's a very important hypothesis. I want to live through today, okay? And I would like to be 100% certain that I'm going to live through today, but the fact is, you can never be 100% confident. And I will explain that to you shortly when we get into the curves. But the very best I could settle for is 99.9 whatever percent confident. Actually, what I have there is 999,999,999 out of a billion chances that I will live through today. Those are pretty good odds. Actually, my odds are probably not quite that good. Now, here's a hypothesis. I will win 1 million dirham today. Now, a million dirham is 1,000 of these 1,000 dirham bills. A million is 1,000,000. So how confident would I want to be? Well, if I were even 50% confident that this would happen, I would be rejoicing, because 50% confidence is 50 out of 100 or 1 out of every 2 times. So since it's really not likely that I would get it, you couldn't say, well, that's impossible. You have a 0% chance of winning 1 million dirham today. Well, anything could happen. It's not very likely. My chance of winning 1 million dirham today might be perhaps 1 in a billion. But you never can have exactly 0%, nor can you have 100% certainty. Here's another hypothesis. This strategy will improve production. Perhaps we want to improve the wind turbine or the grid substation, or the electrolyzer or the water storage. That we have an idea and we want to check to see if that improves, and we want to examine the hypothesis, and we want to be fairly certain that that hypothesis is true, that it does improve. How certain would we need to be? Well, being even 90% confident that this would happen would be very powerful. Would be very pleased to be 90% confident that my strategy would improve production. 90 is 90 out of 100 times, or 9 out of 10 times it would work. Several confidence levels are very common in research. For instance, in medicine, you might have 99.99%. In medicine, it's kind of like that life or death thing of living through today. When we treat a patient, we don't want any of our patients to die. And we want to ensure that the medicines work and do what we say they would do. So we might want to be very, very confident when we're dealing with medicine. When areas of extreme concern, 99%. Production, we might want a 98% tolerance. In education, one of the common levels is 95% confident. In other words, we have 5% error. We're wrong 5% of the time, we're right 95% of the time. If we're talking about an educational strategy and we want to see that it works, being 95% correct would be very acceptable. And in a lot of non-critical areas, we might simply want to be 90% correct. So these are important rates, 99.99, 99, 98, 95, and 90% confidence. Now, in order to understand what these confidences look like, let's examine 90% confidence. Here we have a standard normal curve. You know it's a standard normal curve because the mean is 0, and here are the standard deviations. 1, 2, 3 above the mean, 1, 2, 3 below the mean. Now, let's look at capture a portion of the population, say 90%. What we want to know is, where would our boundaries have to be with z-scores that would allow us to trap 90% of the population in the curve? Now, that 90% is balanced on the mean, and that means some very neat things. If it is balanced on the mean, then that means that this area here, and this area here are exactly the same. In other words, the 90% is here, so what's left is divided in half on each side. Now, how much is left? Well, what's on that side is the same as that side, and together we know that if 90% is in here, that leaves 10%. So we call this the confidence area, and this is the error. Now we represent that with symbols with a lowercase Greek letter alpha. Alpha is 10%. That reads the error is 10%, and of course that means 5% is on each side, so we have 5% here, and we have 5% here. Now notice that I said alpha over 2. We divided the error in half, put half here. We divided it in half, put half there. And together we have 0.05 error on each side, and we have 90% confidence. Now, can we find the z-scores that would let us have 90% in here and allow a 5% error on each side? Now, what's interesting in this is that, yes, we can find the z-scores, but we can be very creative, or we can work very hard. One of the things that you learn to do in statistics is to work smart. We know that this z-score and this z-score are actually the same distances from the mean because it is perfectly balanced. That means that this z-score is positive, this z-score is negative, and we could represent it by this up here. If this was a negative 1 point something, then this is positive 1 point something. Now examine this picture just a minute, and let's ask ourselves, what do our tables give us? See, what do our tables give us? Our tables give us the area from here back. So if we find this z-score, it's going to be very easy. If we find that one, we're going to have to find all of the area from there back. So let's look at the negative one just a minute. And if we trap it, then we automatically have this one, because if it's negative something, that's the positive equivalent. Our error, again, is 0.05. Let's go find 0.05 in the table. So we would go to the negative tables, and we would look for an area of 0.05. And here I've identified it for you. But if you notice, 0.05 is in the middle of negative 1.64 and negative 1.65. So we might interpolate and call that negative 1.645, since it's directly in the middle. Now what that means for us is that with our z-score boundaries of negative 1.645 and 1.645, we have trapped exactly 90% of the data in the interval. Now let's look at some other confidence levels. Now here's a table that I hand out in class, of course, and it's a level of confidence. If we want to be 70% certain, then the areas are 1.04, the z-scores are. Negative 1.04, positive 1.04. I'll show you that. 75% is 1.15. 80%, 1.28. 85%, 1.44. 90%, 1.645. 95%, 1.96. 98, 2.33. 99, 2.58. Now let's play with that just a minute. Let's examine a 70% confidence interval. A 70% confidence interval, of course, has 30% error, which means you have 15% on each side, and if you look up 0.1500 in the table, you find that it's negative 1.04. Let's look at 80% confidence. 80% confidence has 10% on each side because it's 80 plus 20. The 20% is divided in half for error, and the z-scores are negative 1.28. 85 goes to 1.44 and negative 1.44. 90 goes to 1.645 and negative 1.645. 95% goes to 1.96 and negative 1.96. 98% goes to 2.33. And 99 goes to 2.58. Now let me run these back just a minute. And I want you to notice a phenomenon. As we become more and more confident, what happens to our interval? It gets bigger and bigger, doesn't it? As we become less confident, our interval grows smaller and smaller. Now the idea here is that to ever get to 100% confidence, we would have to have the entire curve. To ever go to 0% confidence, where we were absolutely, then we would have nothing under the curve. So you can't have 0%, nor can you have 100%, because there's always a chance that a random act might occur. Now, let's move on with this just a second, and we'll go to the next level of video. I want to thank you very much for your support. I hope you're getting a feeling for what confidence intervals are, how you might use your table to establish confidence intervals, and then we just need to do a couple of other neat things and we can walk with power through this material. Again, in closing, may the odds be ever in your favor, unless, of course, you and I are in the same competition, then it's every man for himself. You have a great day.